So my package is Python chess. It's basically it's version 2.17, stable in Python 2 and 3. You pip install it, and then use Jupyter Notebook to run it. And then this is what Anaconda prop looks like when you pip install it. And then it's actually pretty fun. You import the chess, and the board just shows you like a clean board with like initial, and then it tells you the list of legal moves. So I just briefly listed in color coding what the legal moves are. The knights go in the purple and the blue and the orange and the green, and right here the ends, and then the yellows are the pawns, and then the greens are the pawns again, like depending on what moves you want. And then like if you want to ask if it's a illegal move, then you just ask if it's illegal, and then it says false because you can't just take a rook and take the rook over there. So it's like A2, A1 is illegal. It's basically the SAN is standard algebraic notation for chess, and what it means is the SAN notation is pawn has no prefix. The rook, knight, bishop, queen, king, check, and capture have prefixes and suffixes to dictate what's going on. So for example, if the different knights are taking the same pawn, it's more of the algebraic SAN notation is stated. So for the blue, it's knight from the E column, and then it takes that captures the C3 pawn, and then if it's the purple, it's the knight from the B column takes the C3 pawn, and if it's queen, you could check it while taking the queen at the 8th row, or you could go check at the 7th row without eating the other queen at D8. That makes any sense. Anyways, basically you could do a push board, and then you could print board to show a an actual board where you visually see it, or you can see it with ASCII, basically notation, what's going on, and then you do like a export of the fen to show what's going the notation of the board, and that's universal. So anyways, when you do board pop, you undo the move, so that the knight goes back. When before the knight ate the pawn, if you do a pop, the knight goes back. And then if you write board stack, basically the purple shows the last move, which was pawn going forward. And this is UCI. UCI is a different notation from SAN. It's UCI is basically how the computer reads it from it's basically if it's B2 to B4, that means it's going from B2 to B4 without if it's eating it, then it eats it automatically without the notation of checkmate or X. Anyways, so if you push it, you could ask if it's checkmate, and it's false because the king can either eat the queen or the king can escape with the the yellow or the green. And then basically from here, you could actually if you import random, you could use a random choice generator to list the board of legal moves, and then you can move the king either to the green or to the yellow, and then you randomly push it so that and this generates a random move of the allowable moves on the board. So, and then the code is basically, you could program in Python to generate a random game, and I could just like illustrate that right here. It's basically like the board could play against itself from a list of random moves. So this is what it looks like. So it's pretty cool. I mean, it usually goes into stalemate because the AI is very terrible, and then it just goes mostly to stalemate with the black or the white checking, getting the king once in a while. And right here, this is a draw. Even though black overpowers white, it's a draw. So that's basically a claim as an output. And then this is a distribution curve of the total number of moves generated. Mostly draws are 84%. The black wins 7.71%. The white wins 7.72% of 500,000 outcomes generated from just random moving. And this is basically a zoom in of the wins. So the expected value of black winning in this distribution curve is 49%, with the white winning 50%. So it's a slight, white has a slightly advantage over black, and then you can, figure out if it's significant with the p-value and all of that. And this is like, you could download and figure out what it does with the code. And I have the code right here if you want to play with it. It's pretty cool. And that's my presentation.